Hey, we're going to be covering chapter 7.3 and 7.4. These are going to deal with logarithms. We're going to be concerned with Euler's number, which is the natural log, and then we're going to evaluate and graph logarithms. So section 3 of chapter 7 is titled Use Functions Involving e, and e is a lowercase italicized e, which is the natural base, so also known as Euler's number. That's how you pronounce what looks like Euler. And it is irrational. So that's all we know about it. It's not very specifically defined until we use it in a formula. So we have 1 plus 1 over n raised to the n. And this number approaches e as n increases. More specifically, as n approaches positive infinity, so this is the same thing as n increasing. So as n approaches positive infinity, 1 plus 1 over n to the n, which is Euler's number, approaches e equals 2.718, etc. So this is just giving a basic definition to how this formula works in terms of e and n. So the natural base exponential function is y equals a times e raised to the r times x. And we're going to be going over exponential functions later on. But basically, this is the same concept as an exponential growth function. So if a, which is a constant, is greater than 0, and similarly r is greater than 0, then our natural log, or our natural base exponential function, is an exponential growth function. And if a is greater than 0, but r is less than 0, then we have an exponential decay function. So in terms of sketching out a graph, this would look something along the lines of this. And a decay function would look like this. So if we're told to graph y equals e raised to the negative 0.75 times the quantity x minus 2, let's identify the components of our function. So our e is our value with a being 1. And we know a is 1 because we actually can't see a. Now if a were 2, say, we'd have the 2 in front of the e. But remember, when we have 1, it doesn't show, so it's a ghostly or invisible 1. So we have a equals 1. R is, or I can do that in a different color. R equals negative 0.75. And because this is negative, we can identify this is going to be an exponential decay function. So in terms of actually graphing this, we would go through the same steps that we would for an exponential decay. So I'm not going to actually graph it, but if you review that from our previous sections, then you'll see how this applies in much the same way. So like we had the compounding interest last section, this section we have continually compounding interest. So instead of compounding a certain amount of times a year, this is continually compounding, or continuously, excuse me. Same concept. So our formula for this is a equals p, which again is our principal, times our e number, Euler's number, raised to the r times t. The r is our annual interest rate. As a decimal, and t once again is time. So we have a problem. You deposit $4,000 in an account that pays 6% annual interest, compounded continuously. What is your balance after 1 year? So we're going to plug these values into our formula. I'll copy down the formula below. A equals p times e raised to the t. Excuse me, p times e raised to the rt. So for our principal, let's plug in 4,000 times e raised to the 0.06 times 1 year. this approximately is $4,247.35. And you're going to be using a calculator to approximate this value. The key concept really is knowing the formula and how to plug into it. So, section 4, evaluate logarithms and graph logarithmic functions. A logarithm of y with base b takes this form here. Logarithm y, you can see the base is lower, so therefore you can remember that's the base. And if and only if b to the x equals y. So these forms are interchangeable, and I'm going to be using some examples next so that you can really see how we can move back and forth between these two forms. So say we have log base 2 of 8 equals 3. This is in logarithmic form, but in exponential form, this is 2 to the third equals 8. You can see we have 2 as our base, that corresponds. We have 3 as our x, and 8 is our y. Now let's use another example. Log base 4 of 1 equals 0. Therefore, 4 to the 0 equals 1. Next, log base 12 of 12 equals 1. 12 raised to the first power equals 12. Finally, log base 1/4 of 4 equals -1, because 1/4 to the -1 equals 4. So in solving a problem, we're going to be told to evaluate log base 4 of 64. This equals 4 to the something equals 64. We know that 4 to the third is 64. So therefore, log base 4 of 64 equals 3. Next, we have log base 1/5 of 25. We know that 1/5 to the -3rd equals 125. Oh, excuse me, this is supposed to be 125. So 1/5 to the -3rd is 125. Therefore, log base 1/5, 125, equals -3. Going back to our natural log, or Euler's number, from the previous section, we can apply this to our logarithmic form by saying that lnx, ln being our natural log, is the equivalent to log base e of x. So let's cover the inverse properties of logs. We're told to simplify 10 raised to the log 4. Now, when we have simply log 4 and we're not shown the base, we can assume that the log base is 10. Therefore, this is equivalent to 10 raised to the log 10 raised to the log base 10 of 4. And if we have 10 raised to the log base 10, that is equivalent to simply 4. If we have the same number as is the base of our log, these effectively cancel out. Now we have log base 5 of 25 raised to the x. So we have this equivalent to log base 5, and 25 is the same thing as 5 squared. So we'll just write that as 5 squared, and once again raised to the x. Now that we have the same type of problem as before, in which we have the same base of our log as is the base of this exponent, these can cancel out and we have simply 2x. So once again, these are canceling out, 4 and 2x. Finally, we're going to be talking about graphing logarithmic functions. And think in power functions, because logs are really just exponents. So this first graph on the left is a graph of g of x equals b to the x, and f of x equals log base b of x. There's an asymptote here, and this is the graph of f of x equals log base b of x, as I just said, for b is greater than 1. For example, we could have f of x equals log base 8 of 25. On the right here, we have f of x equals log base b of x, but this time b is in between 0 and 1. So we could have f of x equals log base 1/5 of 125. We had this as an example before, and this is what its graph would look like. Instead of two graphs in a kind of hyperbola, we have this graph here and this here.